These are the most important three equations that we've talked about so far. So these are the equations for 1D kinematics of particles with constant acceleration. So this doesn't work for everything, but the kind of problems we're going to do in this class have constant acceleration. So I'm going to define a few variables, the meaning of a few variables. So position sub I, velocity sub I guess those are the only two. Let those be the position and velocity when time is equal to 0. So when Pi and Vi occur in these equations, it means those are the position and velocity at time equals 0. And PF and VF are the position and velocity at time TF. So with those definitions, the velocity final, VF, so that's the velocity at time final, is equal to the velocity at time equals 0 plus A times TF. The second equation says PF is equal to P sub I plus V sub I times TF plus 1/2 A times TF squared. And then the last one says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And the rest of the problems that we're going to do with 1D particle kinematics are going to use these three equations. And so I'm going to first write out a set of steps for using these, and then I'm just going to do a bunch of example problems so you can sort of see how you go about it. So here are the steps for using these constant acceleration equations. Okay, so the first thing you have to do is you need to make the choices, and these are related to, I said before you can graph position versus time, you have to choose time equals 0 and a position equals 0 in a positive direction. This is related to that, although we're also going to have to choose what time final means, so that's going to be a fourth thing. But we have to choose a location corresponding to position equals 0, a direction corresponding to positive, an instant corresponding to time equals 0, and an instant corresponding to time final. These two are up to you. That's totally arbitrary. These two, there are right and wrong answers for these. And if you choose them wrong, you can't do the problem. So these choices have to be based on instance where you're given information or you want to find information. Okay. Choosing those instants is crucial. Like, you get those wrong, the problem, you're done. You can't go any farther than that. The other two are up to you. That's the first step. Second, the variables that appear in these equations. So those variables are TF, A, TI, TF, VI, and VF. So that's 6 total variables. And if you look back at those 3 main equations, none of them include all 6. They're all missing certain ones. But these are the only variables that appear in any of those. List which ones you know. And which one or ones you want. Well, let's just write that as a single one. We'll think of doing these problems one at a time, so you're always just trying to solve for one of those variables at a time. So, for example, there could be a problem where the way the problem's written out, you know the acceleration, you know the velocity when time is 0, you know the initial position, the position when time is 0, and you know the final position. And the thing you're trying to calculate is the final velocity. Now the third step, and hopefully, and probably most of the time, the last step is you're going to look for one of those 3 constant acceleration equations that has the variable you want, and where all the equations other variables are known. If you can find an equation like this, then you can solve for the variable you want and you're done. And solve. So how does this work out? Well, you can't use an equation to solve for a variable that doesn't appear, right? So obviously, the variable that you're looking for, that you want to solve, has to appear in the equation you use. And a single equation can only let you solve for one variable. So that's why all of the other variables that appear in the equation have to be known for it to work. Okay. There's no guarantee that there's going to be an equation like this. Most of the time there will be. But if there isn't one like that, if no equation works in step 3, try finding an equation that lets you solve for another unknown variable. Usually that's going to be either time final or acceleration. And then go back to step 2. Okay, so that's pretty abstract right now. We haven't done any problems with it, but does anybody have any questions before we start applying this to problems? All right, well, let's just do some examples and get some practice. So the first example. So let's say a car is traveling 40 meters per second and hits the brakes. And let's say that it takes 30 meters for the car to come to a stop. What's the car's acceleration? The first step is to make those 4 choices. The 2 instants. So where are we gonna turn on the stopwatch, and where are we gonna click the stopwatch off? The time equals 0 and the time final. And those are the really crucial ones. Okay, so if we choose the wrong 2 instants, we can't solve the problem. And then the other 2 we have the freedom to choose what we want. So look at this and think about the two instants. We want to choose those based on where we have information and where we want to find information. In this case, the thing we want to find is the acceleration, which kind of occurs over the whole thing. So that doesn't help too much. So really, in this case, what we want to think about is where we're given information. So how would you describe the two instants where we have information? When it stops, so that's going to be the latest instant, right? So I'm going to call that time final. I'll put it down here. And what are the things that we know at that point when it stops? That's right. It's traveled 30 meters. And we know one other thing. When it's at rest, the velocity is 0, exactly. And what's the earlier instant where we have some information? When it starts hitting the brakes, that's right. So time equals 0. Is when the car hits the brakes. And what we know there is we know that once we choose our directions, we're going to know the velocity. It's either going to be positive 40 if we choose our positive in that direction, or negative 40 if we choose the opposite direction. Okay, so now we have to choose the position that we're going to call 0. That's not the same thing as choosing the position when you turn on the stopwatch. That's an easy mistake to make. We can choose anything to be our 0 position. We could choose 1.5 miles away from the start of where the car hits the brakes. Like, that would be sort of pointlessly complicated, but it wouldn't keep us from doing the problem, you know? So, okay, what do we want to call our position equals 0, our reference position, our reference location? Someone choose before someone chooses 1.5 miles away, because then we'll have to convert to meters and everything. Okay, so yeah, let's say position equals 0 is the car's location at our time equals 0. And that is not what this has to be, but often we're going to make that decision. Okay. And then what do you want to call positive direction? Okay, the direction the car is going. And now that we've made those 4 choices, we're going on to step 2, and that's to think about what variables we know and what variables we want. And let's just go through the list. Let me erase these. Okay, so the list of variables is TF, A, PI, PF, VI, and VF. And let's just go through one by one. So TF, do we know the elapsed time between when the car hits the brakes and when it comes to a stop? Nope, don't know that. So that doesn't go anywhere. And do we want it? No, we're not asked for it. So if we can solve this problem without calculating T final, we're happy to do that. Okay, so that's nowhere. The acceleration, do we know that? Do we want it? Yeah, that's the one thing we're asked for. That goes over here. The initial position, do we know the car's position when time is equal to 0? Yes, because that's where we chose our position equals 0 to go. Okay, so when time is equal to 0, the car's location is 0. So PI is equal to 0. Do we know the final position? Okay, so we know it's 30 meters away from the initial position. And now we have to think about, is it positive or negative? We chose our positive direction to be the direction the car is moving. So is P final going to be plus 30 or minus 30? Yep, plus 30 meters. Do we know the car's velocity when time is equal to 0? We do. We know that its speed is 40 meters per second. That's way too fast to drive, by the way. That's not safe. Okay. So that's one to grow on. That's like probably 90 miles an hour. I don't think you can stop, now that I think about it, in 30 meters. You'd have to have pretty good tires. Okay, so the initial velocity, so we know the speed is 40 meters per second, and then we have to think about the sign. So the sign of the velocity is the direction that the thing is moving. Is it moving in the positive or negative direction? Positive. So V initial is positive 40 meters per second. And then the last one is, do we know the final velocity? When the car comes to rest, rest means 0 velocity, so this is equal to 0. And now we need to go back up to those 3 equations and look for one of them. We're hoping one of those has A in it, and everything else that's in it is known. Okay, so we know both positions, both velocities, and we want the acceleration. So let's look back at these one by one. This first one, A is in it, so that's good. But TF is in it, and we don't know that one. So we can't use the first one. There's 2 unknowns in it. You can't use one equation for 2 unknowns. The second one, A is in it, so that's good, but TF is in it again, so we can't use that one. And then the last one, A is in it, that's good. And then what else is in it? We know that, we know that, we know that, and we know that. So this is the one that'll work in this case. And we don't have to go on to try to find an intermediate variable and go through the whole process again. So the equation that works is 2A times the quantity position final minus position initial is equal to V final squared minus V initial squared. Works. Hey. And so now I'm going to put all this stuff in, and I'm going to keep the units as I do it. Up through the first test, I want you to keep your units in all your calculations, and I'll show you how to do that. But first, I'm just going to write them in here. So we have 2 times A times the quantity, P final is 30 meters, minus P initial is 0. And that's equal to the velocity final squared. You don't have to put units on zeros. I'm just leaving zeros as zeros. Minus the initial velocity of 40 meters per second squared. And now I'm going to write out this equation in the same form that I used when we did unit conversions. So anything in the numerator is going to be above the fraction bar. Anything in the denominator is going to be below. And so here we have on this side 2a I'm going to do the subtraction. 30 meters minus 0 is 30 meters. So that's the left side of the equation. And then on the other side, we have 0 minus whatever this is. So that's, notice we do the square before we take the negative so that we have the negative. And then we have, so you can square it all right now, or you can, so 1600. And we also have meters squared over seconds squared. I'll write that as meters times meters over seconds times seconds. Any questions yet? And now it's just algebra. You can treat the units as algebraic variables. We're trying to get a by itself. So first, let's divide both sides by m. We can get rid of one of those. And then second, let's divide both sides by 2 times 30. So divide both sides by 60. And we have a over here is equal to negative 1600 meters over seconds times seconds divided by 60. And you get that the acceleration is equal to, I use different numbers. Can someone divide that for me? So you get negative 26.7, and the units are meters per second squared. And so notice it's sort of cool how this works. If you go through the steps like this and keep your units all the way through the calculation, the answer you get at the end is going to be the right units for the thing you're looking for. Acceleration needs to be meters per second squared if you're using SI units. Yes? The units thing? Yeah, for now you do. In not too long, I won't make you do that anymore, but we are going to do it for a while. That's a pretty big magnitude of acceleration. 26.7 is almost 3 Gs. So I don't know if that's realistic. But let's think about the sign. Does the sign make sense? It does. And the way to think about it is the car is moving in the positive direction. The velocity is positive. It's slowing down, and that means that the velocity and the acceleration have to have opposite signs. Okay, so since the velocity is positive, we know the acceleration has to be negative. And you can always think problems through like that. So the negative sign makes sense because velocity is positive and it's slowing down. Okay, I'm going to do this problem again, but this time I'm going to make different choices of the position equals 0 and the positive direction. Okay? And we'll see, what kind of things are different, but we'll see what kind of things give us the same information too. So this time, our position equals 0 is going to be at the location where the car comes to rest. And our positive direction is going to be opposite the car's motion. What about the two time choices? Can I change those? No, those are just either right or wrong. So the times you can almost never do the problem because usually they only give you the minimum amount of information you need to solve it. You have to make the right choices about those two instants. The position and the direction you can change and still do it. So well for I guess the answer to that is that drawing those position versus time graphs is a little different in that way than using these equations to come up with. Yeah, right. So you can do that for the position versus time graphs, but you can't do that if you're using these equations to solve for variables. So okay, the steps. First step, that's already decided. So time equals 0 is when the car hits the brakes. Time final is when the car reaches rest. Position equals 0. That's the location where the car comes to rest. And the positive direction is opposite the car's motion. And now out of this list of 6 variables, time final, acceleration, position initial, position final, velocity initial, and velocity final. We want to figure out which ones we know and which ones we want. Okay, so first, do we know time final? No, we still don't know that. Do we know the acceleration? We're still trying to find that. We know the initial position. We do, but it's not as simple as it was last time. So now, if you think about the motion, here's where, so the car is still going this way, right? This is where the car hits the brakes. This is where the car comes to rest. This is our 0 position. And this is our positive direction. The distance between these two spots is 30 meters. So what location are you at if you start at 0 and go in the positive direction 30 meters? Plus 30, yep. And, you know, if we think of this, do this like those pictures we did in the problems like with the swimmer on the beach and swimming here and there and whatever. This diagram's pretty simple. It just starts out here and ends here. So all this is saying that the initial position, yes, we know what it is. It's positive 30 meters. Any questions about that? So this is where the car is when time is equal to 0, and it has the label positive 30. Do we know the final position? The position when time is t final? Yeah, 0, right. Yes, that's right. What about the velocity at time equals 0? Do we know that? At time equals 0, that's when it's going 40 miles an hour. But now we have to be careful with the sign again because it's going 40, not 40 miles an hour, 40 meters per second. It's going 40 meters per second this way, but now that's the negative direction. Okay. So the velocity at time equals 0 is negative 40 meters per second. And then do we know the velocity at time final? 0, yep. And now we're looking for an equation that works with this stuff. It's going to be the same equation because we know all the same stuff, but the numbers are all different. So this works again. Okay, so we have 2a times the quantity 0 minus 30 meters is equal to 0 minus the quantity negative 40 meters per second squared. And it's important to notice that you're squaring the initial velocity, and the initial velocity is negative 40. So that negative, this negative, goes inside the parentheses. Okay. That's important because what happens when you square a negative number? You get a positive, so that sign is going to disappear. So if we multiply, well, so we have 2a times the quantity negative 30 meters is equal to, so this is positive 1600, and then you take negative of that. So negative 1600 meters squared per second squared. And now I'm going to write it out in that format for converting units. So we have 2a times negative 30 meters is equal to negative 1600 meters times meters over seconds times seconds. I'll cancel 1 meter on each side there. And now I'll divide both sides by negative 60. And we get A is equal to positive 26.7. Is that what it was? meters over seconds times seconds. So A is equal to 26.7 meters per second squared. Is that the exact same answer we got before? No, the magnitude's the same. Okay, we got the same magnitude of that acceleration, but the sign was different. Okay, but now think about pointing in the direction of what a positive acceleration means. Okay, what we got here is an acceleration of 26.7 going in that direction, right? Because the positive direction is this way. Last time we got negative 26.7, but our positive direction was this way. So again, if we think of it that way, in both cases, we got an acceleration of 26.7 that way. So even though the signs come out different, the meaning of it is the same. I'm going to go up here and write that. Okay, so this is acceleration is negative 26.7 in the first example, but you can think of that as 26.7 meters per second squared this way. And now think about it in terms of speeding up or slowing down. Does it make sense that we have a positive acceleration in this second time through? Yeah, because the second time through, our velocities were all negative. And if this thing's slowing down, which we can't control, that was given in the problem, it's slowing down until it stops. The acceleration and the velocity have to have opposite signs. So it has to be positive because it's slowing down. And the velocity was negative. Okay, let's do another one. So let's say there's a ball rolling down a ramp. And when it gets to the point A, so at the point A, the speed of the ball let's say it's going 2 meters per second. And 1 second later, it's reached point B. How far away are those? Let's say 1 meter away. So first, what's the acceleration of the ball? I don't know. I can't do that in my head. I don't know. I can't do it in my head. And then second, what's the velocity at this point v? Okay, so let's just go through all the steps. So step one, we have to make those choices. So first, let's do the times. Time equals 0 and time final. So what do we want to call our time equals 0? Yeah, the instant passes A. And why do we want to choose that? It's easy because that's where we are given a bunch of information. We know the speed there, we can turn that into a velocity. We know the position in comparison to B. So we're given information there. And what do we want to call time final? Yeah, the instant passes B. And now the choices that are up to us. Position equals 0. Yeah, I think probably the simplest one is to choose A, but we could choose B if we wanted to. But so another way to say this is the ball's location or position, time equals 0. And that seems like sort of a cumbersome way to write it, except if you think of it this way, it's clear that choosing your position equals 0 at the object's location at time equals 0 makes p sub I equal to 0. So that's sort of a helpful thing to notice. This is going to mean that p sub I is equal to 0. And then the positive direction, down the ramp. Yep. I mean, either one's fine, but that makes sense to me. And now we'll list out the variables: time final, acceleration, p initial, p final, v initial, v final. And we're going to figure out which of those we know and which ones we want. Okay, so time final. Do we know that? Yeah, we do this time. What's that? Okay, 1 second. Do we know the acceleration? That's the first thing we want to find. Do we know the initial position? Yep, that's 0. Do we know the final position? One meter. Do we know the initial velocity? Uh, 2 meters per second. And is it positive or negative? So the speed is 2 meters per second. Is the velocity positive or negative? Positive, because this direction is positive, and that's the direction it's going. You just take the speed and tack on the sign depending on which direction it's going. So initial velocity is 2 meters per second. And then do we know final velocity? No, we do want to find that, but let's worry about that next. Okay. So for this part of the problem, we'll say we don't care about that. All we care about at first is calculating the acceleration. All right, so are there any of those three equations that work for these? So what do we have? The two positions, the initial velocity, and the time, and we need acceleration. So going back to these three. Having acceleration in the equations is the one thing that's no problem. That appears in all three of these. So let's try the first one. We have acceleration. Do we know all these other three variables? No, we're missing this one, so we can't use the first one. The second one, we have acceleration. Do we know time final, v initial, p initial, and p final? Yeah, so that one will work. So this equation that says p final is equal to p initial plus v initial time final plus 1/2 a time final squared. That one works. Now I'll fill this stuff into the equation. We have 1 meter is equal to 0 plus 2 meters per second times 1 second plus 1/2 a times 1 second squared. So this says 1 meter is equal to, notice these 2 seconds cancel. If you want, you can write out each piece in the, that bar notation and to cancel stuff. But so 1 meter is equal to 2 meters plus 1/2 a times 1 second squared. The first thing I'm going to do is subtract 2 meters from both sides to get that a term by itself. So we have negative 1 meter is equal to, and now I'm going to use that other notation. So we have 1/2 times a times seconds. And I'll multiply both sides by 2. So now we have negative 2 meters is equal to ASS. That's rude. And then I'll divide both sides by seconds squared, and we get negative 2 meters per second squared is equal to A. And okay, well, that's funny. So what we really have, that's okay. Hey, don't worry. Does it say? You just drew it wrong. But I have proof here that I drew it right. Okay, so it's, here's A, here's B. Right, that would be odd. I suppose there's ways that could happen, but Okay, so it starts out going like this. Now all the numbers work, but if you change it like this, now it makes sense that the ball's slowing down as it goes from A to B. Okay, so, well, does it make sense that A is negative? Well, now it does, now that I changed the picture. The velocity is positive. So the negative acceleration means that it's slowing down. Yes. Given what? Yes, those will always be on the test. Okay, so now for part B, we want to calculate the final velocity. We can keep all the same instance because that final velocity we want is at one of our two instants. So V final is already at our T final, so we can still keep those. So let's keep everything the same. Our time equals 0, our time final, our position equals 0, and our positive direction, those are all the same as in part A. And if those are all the same, then the stuff we know, the stuff we knew in part A, we still know. So we still know time final is 1 second. Now we know the acceleration too. We just solved for that. That's negative 2 meters per second squared. The initial position is 0. The final position is positive 1 meter. The initial velocity is 2 meters per second. And we want to calculate the final velocity. So you have to use the, yeah, some of you could do this in your head, that's right. Oh, I see what you mean. Yeah, because you know it's 1 second, and yes, that's right. So, so we have the equation 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. That's the one that works. That one doesn't have V final in it. Oh yeah, it does. You're right. So let's use that one actually because it's easier. Yeah, always take the easy way. So V final is equal to V initial plus ATF. Just give me 2 more minutes. V final is equal to 2 meters per second plus negative 2 meters per second squared times 1 second. And so that's equal to 2 meters per second minus 2 meters per second. And so V final is 0. Well, I was lucky because if I would have made those distances any farther apart, it would have not had a solution and been all confusing. Okay, but so that is exactly the point where it comes to rest. And then if you went any more time, it would start rolling back down the hill.